Okay, we're going to look at a couple sample problems here. So the first one that we're looking at is this situation where there's two blocks, one that's hanging with a little mass m, one that's sliding along a frictionless table with big mass, big M, and it's going over a pulley, and the pulley is frictionless, and we're assuming that the rope is also massless. And those are important assumptions, but those are assumptions we're going to make. So the question is find the acceleration of block S and block H and the tension in the cord. Well, the first thing for us to think about is that block H and block S, if we kind of create this closed system, they're going to be accelerating at the same rate. Think about that. They must be accelerating at the same rate. Otherwise, the rope would become slack. We know that the rope is going to be tense, so that every piece of the rope is accelerating at the same rate. So the two masses must be accelerating at the same rate. So this is going to be equal. Okay, well, if we think about the forces that we have going on, the hanging mass has the force of gravity pulling it down and the force of tension pulling it back up. And that same force of tension is pulling this mass. And let's do these in red. What other forces are acting on the big mass, or on block S, rather? So on block S, we have the force of gravity pulling it down, but there's also the normal force pushing up from the table. And we know that the force of normal equals negative force of gravity. So those cancel each other out. And we know that the tension force pulling block S is equal but opposite to the tension force pulling block H. So those tension forces here and here in the whole system cancel each other out. So the net force then is just the force of gravity, which is little mg. And that net force is what's accelerating our whole system. Well, we know that net force equals mass times acceleration, but the mass here is the mass of the entire system. It is big M plus little m times A. And that net force, well, we found that. It's just little mg. So therefore, we can set up our equation that the net force, which is little mg, equals mass times acceleration. So big M plus little m times A. So my acceleration is going to be m plus little m. Oops, let me rewrite that. Dividing, we have mg over big M plus little m. And this makes sense if you think about it. You know, if block S, if this block here were to disappear, then this mass would be 0, and the acceleration would just be gravity, which is what we would expect for hanging block H if it didn't have block S kind of holding it back. So in other words, you know, if block S disappeared, if all of a sudden we cut the rope, the acceleration would be mg over 0 plus m, which is just g. So what we're saying is if we were to just snip that rope right there, that's what we would get. Okay, well the next question is a particularly interesting one. It says, what is the tension in the cord? Well, let's see if we can get this drawing a little bit bigger here. So going back to this drawing, what we know now is that the acceleration, equals mg over big M plus little m. And if we now look at just this system, if we kind of ignore the big block for a second, so if we just focus in on block H, what we know that for block H, the two forces that are going on are the force of tension and the force of gravity, so little mg. And so when we just focus in on this system here, the tension is real. The tension won't cancel out like it does if we look at the entire system. And that's going to help us find the tension in the cord. Because now what we know is that the net force on just block H, if we're just looking at block H, the net force equals the force of gravity minus the force of tension. And the net force is resulting in a mass times acceleration. So the net force is our mass times acceleration, which is mg over big M plus little m. That equals mg minus the force of tension. Therefore, we get that the force of tension equals, just solving this equation for force of tension, equals mg minus m times mg over big M plus little m. And so the key sort of the technique that's really important as far as doing these physics problems is that we can change the system about which we're looking. So at the beginning we wanted to look at the entire system. So we were looking at I know it's a little bit messy here, but we were looking at this whole group. And that let us figure out acceleration. Then we wanted to just look in this region so that we could investigate tension. So you have that freedom, that ability to choose the system so that you can look at external versus internal forces. Okay, next type of problem has to do with an inclined plane. But before we actually look at the problem at hand, let's think about an inclined plane. And for right now, let's consider it to be frictionless. So we've got some plane at some angle theta and a block that is on the table. And what I didn't make clear in the last video where we were looking at normal forces, but I'll make clear now, is that the normal force is always perpendicular to the plane. So the normal force is going to be coming out like this. And then we're going to have a force of gravity. And the force of gravity is going to be pulling straight down. Well, what we're going to want to do, we need to break these up into components. And what might be a little bit counterintuitive, but it actually makes the system a lot simpler, is to make our axis like this. So therefore, we're going to need to break down force of gravity into the gravity force that's pulling it down the plane and the force of gravity that's pulling it directly into the plane. So force of gravity pulls it straight down, but we break that component into this force right here that's bringing it down the plane, and this force right here that's bringing it directly into the plane. And if we do a little bit of geometry, what we realize is that this angle theta here is that angle theta. I knew as soon as I said that I make this mistake all the time. That's not the angle theta that we're talking about. Let me redo this, redraw this. So, given this triangle here, we know that this is a right angle there. And this is our angle theta, the same angle theta as we have there. So let's, just to make that totally clear geometrically speaking, let's take a moment to kind of convince ourselves of that. So we've got this point right here. We've got this theta. So this point is our block. It might make it, I think it makes it helpful if we just bring that block all the way there. And then we create our right angle. So that's a right angle, that's a right angle. So therefore this angle here must be 90 minus theta. And if that angle is 90 minus theta right here, and if we have a right angle, then this angle in here must be theta. Therefore, this force coming down, that's the force of gravity that's pulling it into the plane, is mg cosine theta. And the force of gravity that's pulling it down the plane is mg sine of theta. And we will look at the idea of friction pulling it up the plane, but for now we're just ignoring friction because we're assuming it's a frictionless plane. And so what are some things that we know? Well, because our box is staying on the plane, it's not going through it or just projectiling into the air, we know that the normal force must equal mg cos theta. In other words, these forces must cancel out. Therefore, the net force is down the plane, and the net force is mg sine theta. So let's use that idea to think about this problem where we've got a frictionless plane at some angle theta with a block of little mass m that's being attached to a pulley that has a mass of big M that's pulling it down. And what we want to find is acceleration and tension. So we want to find the acceleration of the system, which is going to be constant. The rope and the masses will all be accelerating at the same rate. And we want to find the tension that's in the rope. So just maybe a simpler drawing here. So we've got little m, and we've got big M. And if we draw all the forces, we've got force of tension here, and the same force of tension in the opposite direction there. We've got a normal force, and then we've got its weight, but the force of gravity. But let's put that down into little mg sine theta and mg cosine theta. And if we look over at the big mass, the additional force that we have is big mg. So which of these forces are going to cancel out? Well, we know that the normal force and mg cos theta will go away because they cancel each other. If we're looking at the whole system, which I recommend us doing, the force of tension goes away. And therefore, and let's just assume that this system is moving that way. So this mass is big enough to pull that mass up the plane, and so this mass is falling downwards. Well then, the net force that we have, the only forces left, are these two, working in opposite directions. So the net force equals mg minus little mg sine theta. Well, what we know about net force is that net force equals mass times acceleration. The mass of the whole system, so net force is mass times acceleration, where the mass that we're talking about is big M plus little m times the acceleration of the system equals, well, it equals the net force, that net force being mg minus little mg sine theta. And so very easily then we can just solve for acceleration. Okay, so just like in the last problem, now what we want to do is find the force of tension. And the way that we're going to find the force of tension is just by zooming in on one little section. So let's just zoom in on this. So in that scenario, we've got our big mass M right here with a force of tension pulling it up and force of gravity pulling it down. And so the net force on M, so the net force just on M is going to be big mg minus force of tension. And right now what we're looking for is the force of tension. We want to figure this out. Well, we know that net force is just its mass times the acceleration, and we found the acceleration. And that's going to equal mg minus ft. And so the last step to find ft is just to solve the equation for ft. So we get that the force of tension equals the following. Okay, so let's look at one more problem. The last problem has to deal with apparent weight. So, and it's not like your parent's weight, like how much your mom or dad weighs. That would be a parent's weight, but this is apparent weight. So it's the weight that it seems to be having. And this is a really fun classic physics idea. So you're in an elevator. So you're in an elevator, and the elevator is not moving, so we're going to say the velocity is 0, and here's some person standing on a scale. So they're on a scale. What the scale reads is not your weight, but the scale actually reads the normal force. it reads the force that the scale is pushing back on you to prevent you from, well, falling through the scale. So when we're in this elevator and the velocity is 0, so we're stopped, we've got the force of gravity pulling us down. And we've got a normal force, which is what our scale is reading, pushing us back up. So for this particular case, the normal force equals the force of gravity, but in the opposite direction. The force of gravity, this is your weight. Okay, well, what happens now if all of a sudden the elevator starts accelerating upwards? So now the elevator is going to accelerate, and it's going to accelerate upwards, let's say at g, so at a rate of gravity. So all of a sudden, here you are on your scale. You haven't eaten anything more. You still weigh the same amount. But the scale reading is going to change. Strange. Why? Well, let's think about it. You've got the force of gravity pulling you down, and the normal force that's pushing you back up. And if we look at this closed system, you know, those are the only forces that are acting on you, the normal force and the force of gravity. But you are accelerating upwards at gravity. So the normal force minus the force of gravity, and I put the normal force minus the force of gravity because the normal force is what's pulling you upwards. And just to be clear, I'm talking about like the magnitudes of these. So the magnitude of the normal force minus the magnitude of the force of gravity must equal your mass times acceleration, where the acceleration in this case is gravity. Well, what is your force of gravity? The force of gravity that you have, this force of gravity, that is, so normal force minus, force of gravity is mg, equals mg. So the normal force must therefore equal 2 mg. So if the elevator accelerates upward at a rate equal to the gravitational constant, your scale, the scale is going to show you weighing twice as much. Again, you don't weigh twice as much. You haven't gained any weight. What you're feeling is an apparent weight, which is the normal force pushing twice as much as it normally does. So you will feel heavier. You'll feel twice as heavy, even though nothing has changed. So say you feel really bad about being twice as heavy. What do you need to do? Not go on a diet. No. Just wait for the elevator to go down. Because now the elevator gets to the top floor, and here you are in your elevator, and here's the scale, and you're feeling bad about yourself. But luckily the elevator goes down. And let's just say that it goes down at an acceleration equal to gravity. So now, once again, we've got the force of gravity, which is your mass times acceleration. You've got the normal force, which is the force pushing you back up, which is the force that your scale is reading. And we've got a net force, which is mass times acceleration in the direction of gravity. So that's going to equal Fg minus Fn. Again, thinking about their magnitudes, the magnitude of this and the magnitude of that. So doing a little bit of simplification, we get that ma equals, and this a is g, so that's mg, equals the force of gravity, but the force of gravity is just mg minus Fn. Solving this, we get that Fn equals 0. So in other words, while going upwards you feel twice as heavy, going downwards, if the acceleration is gravity, you feel no weight. You feel weightless. And this is a cool opportunity for when the force, the normal force pushing back on you is actually 0. So you feel apparently to have 0 weight. Weightlessness. Okay, hopefully that was moderately interesting, and those are a couple classic physics problems.